Hello, you're welcome back. All right, so semiconductors. Okay, so this video is introduction. Okay, we're going to be looking at the introduction to semiconductors. So, what are semiconductors? Now, semiconductors are substance or materials, okay, that have partial electrical conductivity. All right, so they have partial electrical conductivity. So they can neither you can neither classify them as conductors nor insulators, but the electrical conductivity characteristics is found midway between conductors and insulators. So here comes the classification of material. Okay, now based on electrical conductivity, we can classify materials into conductors, semiconductors, or insulators. All right, so conductors are those materials that have high conductivity of electricity. All right, basically they are metals that actually offer free flow of current through them. Okay, why do they offer free flow of current through them? Because they have low resistivity or low resistance. All right, okay, but for insulators are materials that have very low conductivity. In fact, they have low conductivity to the extent that it is practically impossible, okay, to have electron flow through them. Okay, so why do they have such low conductivity? Why? Because they have a high resistance to the flow of current. Then now come to the main business of the day, which are semiconductors. So now we say semiconductors are material that have partial conductivity. So they are found midway between conductors and insulators. So now for us to actually illustrate the conductivity of material, we use energy band diagram to represent that. Okay, unlike what we do in chemistry, okay, where we can actually represent the conductivity of a material based on the valence electron. Okay, you can classify a material, whether you can classify a material into metal, non-metal, metalloid based on their valence electron. But in physics, okay, or in electronics, we actually study the conductivity of a material based on energy band diagram. So this is a typical energy band diagram. The very first energy band diagram is that of an insulator. This first one you see here. So according to the energy band theory, okay, we are meant to believe that um, electrons, okay, that actually that is the actual cause of conductivity in any material. The energy of electron can be divided into valence band, okay. So that is the energy of the valence electron in the valence band. Then of course, they now have the higher energy level. So the higher energy level is that of the conduction band. So unlike in chemistry that we only talk about the valence band, okay, different level of valence band. But here in electronics, we believe that for a material to conduct electricity, there's another energy level above the valence band. So this any material can only conduct electricity if electron can actually migrate, okay, into the conduction band. So if that material have electron in the conduction band, then that material should conduct electricity. So now this is the energy band diagram of an insulator. And as you can see here, the conduction band and the valence band is being separated by a wide energy gap. There's always a gap between the two bands, valence band and the conduction band. So as you can see for an insulator, there's a wide energy gap between the valence band and the conduction band. That is why for an insulator, it's practically impossible to have electron jump, okay, across this wide energy gap and enter into the conduction band. So that is why we say that so insulators do not conduct electricity at any condition at all. All right, then this energy band is for the conductors. Now, what do you notice in this energy band? The energy band, okay, between valence band and the conduction band, discover that they overlap, which simply means that the gap is negligible. Okay, so we have an overlap between the valence band and that of the conduction band. That is why it is just very easy, even at any condition, okay, at a normal condition, to have valence band electron, okay, located at the conduction band. That is why conductors can easily conduct electricity. Why? Because the valence band, okay, does not have any restriction that will cause them not to enter into the conduction band. All right, now remember this topic is about semiconductors. Now let's now look at the energy band diagram of a semiconductor. So we have to clean up now. So now for a semiconductor, the energy band of a semiconductor is such that there is a very there's a gap, but that gap is very small, okay? Small gap, small energy gap. Small energy gap that exists between the valence band and the conduction band. So if that being the case, now we'll not say that okay, our semiconductors are partially, okay, conductors. How do they conduct electricity? What is the condition that warrant them to conduct electricity? Now, the condition that warrant them to conduct electricity is the condition that will enable electron at the valence band to gain energy, okay, that we warrant them to jump into the conduction band. And that condition is basically when the temperature, okay, of a semiconductor increases. So I can say that the conductivity of a semiconductor, pure semiconductor, okay, is dependent on temperature. So as the temperature increases, as I raise the temperature of a semiconductor, then the conductivity actually increases. Why? Because electron at the valence band will gain energy and enter into the conduction band where they will conduct electricity. Okay, so that is why we say that semiconductors have okay have negative temperature coefficient, negative temperature coefficient of resistance. I will tell you exactly what that means. Okay, remember conductivity is the reciprocal of resistivity, or conductance is the reciprocal of resistance. Okay, they're opposite each other. So if we say that um, temperature is proportional to conductivity, that means on the other way around, we can also conclude that temperature is inversely proportional to resistivity. Okay, so that means as the temperature of semiconductors increases, you know what happens? Their conductivity increases, okay, which actually reduces their resistance. So we say that at higher temperature, okay, semiconductors have a very low resistance but high conductivity. All right, now let's analyze how conductivity actually takes place and what actually causes, what is the brain behind the conductivity of a semiconductor as the temperature increases. Okay, so are we still okay? Let me still use this energy band diagram. All right, let me clean up. Okay, let's say at a very low temperature, um the conduction band doesn't have electron. Then we now have the valence band. Okay, the electron are actually filled up. Okay, they are complete. So when you apply temperature to this semiconductor, what happens? Okay, what happened? One electron gets energy and migrates into the conduction band. As it migrates into the conduction band, it will leave that particular position it used to be. Okay, it will actually leave a vacant position. Okay, a vacant position that is deficit, okay, that is that electron is supposed to be, but there's no electron there, is what is known as hole. Remember, electron, okay, let me clean up this so that I will have space to illustrate. Remember, electron are negatively charged, please pardon me, okay? So now, as they actually leave, anytime they leave, they create a vacant position in a place, okay? If they just leave this place, they will now actually create a vacant position known as hole, and hole is positively charged. Of course, the absence of negative charge is positive charge. That's what it simply means, okay? Well, simply put, in chemistry, we're meant to understand that anytime an atom loses electron, are you okay? It becomes positively charged, but let us not go into details. So just take note of the fact that, okay, if electron actually move to the conduction band, they will create a, a hole, okay, which is also a charge, and that charge is positively charged. The electron here, this electron that have actually gone to the conduction band, okay, electron, of course, that's a negatively charged electron. Now, this electron now in the conduction band now is free to actually move, conduct electricity quite well, okay? But another, now, as I said, the electron is free to move at the conduction band, and is very much ready to conduct electricity. In fact, what we know as electricity, the conduction of electricity, okay, of course, that is current, is the flow of current. And what actually causes the flow of current is the flow of charge by the charge carrier. So electron is a charge carrier. So the flow of electron is what we actually cause that semiconductor to conduct electricity, okay? But apart from the movement of the electron, there's another current that will be generated, and that is the current due to the hole. I will tell you how the whole current actually uh, happen, because as the electron is moving, the hole is also moving. Okay, let's see how that happens. Now, you see what's going to happen now is this: as I have this hole, vacant hole here, okay, one electron, adjacent electron, okay, in the same valence band, will move to cover up that vacant hole. As you can see, as it moves to cover up that vacant hole, then itself actually creates another vacant under hole. Okay, then the same thing happen again, same process. This adjacent electron goes again, cover this vacant hole. Okay, and another vacant hole is being created. Okay, so I'm very sure that this one too, this electron at this point can still gain energy, jump into the conduction band. So discover that what actually causes electrical conduction in electrical conduction in semiconductors are two charge carriers. Okay, we'll call them charge carriers, right? Charge carriers, because what they carry charge, one carry positive charge, the other one carry negative charge. Okay, charge carriers. And what are those two charge carriers? Okay, so those two charge carriers include electron, which of course carries negative charge, and of course hole, which carries positive charge in opposite direction. Okay, so electron move forward, the hole move backward. So hole carries a positive charge, and two of them are generated in pairs. Okay, and they are generated due to what? Heat. So that's why if we are being asked what causes electrical conduction in a pure semiconductor, okay, it is due to thermally generated. So thermally generated electron hole pair, okay, they are in pairs because it is the once one is created, the other one is created. Okay, they are not independent of each other. Once electron is actually created, electron jump to the conduction band, then a vacant hole will be created. Okay, so they are in pair. So that is the only thing that actually causes electrical conductivity in semiconductors. Thermally generated, okay, electron whole pair. So just write it down. So now we're going to actually derive formula or write the expression for the conductivity of a semiconductor. Okay, very important. In fact, it's a very important, it's a high point of this particular tutorial. Okay, because of conductivity of a material, that's a formula we use in expressing the conductivity of a material. So this is simple. I'm very sure from the introduction of electricity you're very familiar with this symbol. Okay, symbol for conductivity. So now, so what are we looking at? We're looking at the expression for the conductivity of semiconductors. Then of course, we can also need to find the expression for its resistivity. Okay, as you don't forget that the charge carrier in a semiconductor, in a pure semiconductor, is hole and electron. Those are the two things that actually carries charge. So now, before we get to the conductivity, first of all, we can simply conclude that the current, okay, the current, please pardon me, we can simply conclude that the current of a semiconductor, the current, okay, of a semiconductor is due to the current, okay, as a result of the flow of the electron plus the current as a result of the flow of hole. All right, so it is this electron and hole that contribute to the total current of a semiconductor. Now let's now go to the conductivity. Okay, now the same with the conductivity. Conductivity of a semiconductor is given by the formula NIE bracket open UE plus UH. Okay, don't worry, I'm gonna give you uh the these parameters. Okay, I'm gonna give you the meaning of all these parameters. Of course, you know this is conductivity, electrical conductivity. You know this already. All right, then E is the charge of an electron. Okay, electron charge, which of course is a constant. The charge of an electron, it has a constant value. And what's that constant value? Is 1.6 times 10 raised to the power of minus 19 coulomb. Okay. Then the next is the one in the bracket. Okay. UE. This is mobility of the electron. The mobility of the electron. UE, mobility of the electron. And the other one, okay, UH, mobility of hole. I'm just choosing U to represent it. It's just simple for me to call this symbol U, but it's not U. But just take it. This what matters is the name of the symbol. Okay. So UH, mobility of the hole, because here we are dealing with semiconductor. So both the electron is moving and the hole is actually moving. Okay. So and they are actually equally they equally contribute to the flow of current in a semiconductor. So please take note of this. Okay, take note of that, so that any time question arises that you need to calculate the conductivity of a semiconductor, this is the main formula. Now, in case the question is calculate the resistivity, okay, you know, in electricity, resistivity is always given as 1 all over the conductivity, reciprocal. Okay, conductivity and resistivity, they are reciprocal. So that simply means that if I'm to evaluate resistivity, all I need to do is just 1 all over. Okay, and okay, I have not, there's one parameter that's missing. Please pardon me. The NR. Please pardon me. Okay, this NR is actually represent the density. Okay, charge carrier density, which of course we know that it is not one, two of the, okay, charge carrier density or concentration. So intrinsic conductor Okay, I call it an intrinsic conductor because we'll talk about that. It's a pure conductor. Okay, Ni intrinsic semiconductor, intrinsic semiconductor. Okay, we'll discuss this. Okay, why I call this an intrinsic semiconductor. So here I'm dealing with conductivity of semiconductor. That simply means that it's a pure form of semiconductor. There are two types of semiconductor. Semiconductor in its pure form and the one in its impure form. Okay, so that's why you see me using I here. So this is intrinsic charge carrier of the density or the concentration of the charge carriers of an intrinsic semiconductor in its pure form. Okay, charge carrier density or concentration. And of course, for a semiconductor, a pure form of semiconductor, the charge carrier is equal hole and of course electron. So I hope that is well understood. Okay, as I was saying, so if we are now want to get to the resistivity, that's going to be 1 all over NIE bracket open UE plus UH. And that is the end of the story. Okay, so we definitely will apply this formula. We'll solve question on this. But before then, okay, we're going to talk about the types of semiconductor, and that will be in the next video. All right, see you in the next video. Thank you very much.